All right.
right.
Thanks for taking the time to meet with me, Charles. It's
Thank
good
you.
to see you in person.
Thank you, Kwabena. Thank you. Thanks
Thank
for
you.
driving down here to our office, and it's great seeing you.
Yeah, no, traffic wasn't too bad today. Actually, I guess it's because it's Friday, so it's not a work from
it
the
is.
office day, I
For me,
suppose.
it was the same too.
Yeah,
it was good.
It only took 30 minutes, which was great compared to like an hour
You must
normally.
be driving a supercar.
Yeah. No, not so much, not so much. But anyway, let's get into it.
Sure.
So tell me about Pixar. Where am I at right now?
Okay, so Pixar. This is actually our Sunnyvale office.
Yeah.
Pixar is headquartered in Taiwan, Hsinchu, Taiwan, where all our design work and our foundry actually are all there. So a lot of people know us, Pixart Imaging, as making the best optical mice, right? With like in the gaming community, we are kind of like the sensor of choice for like the really fast, high speed, low latency kind of gaming mouse for the pro industry.
Yeah.
And then the other name that sometimes Pixar pops up is the Nintendo Wii. If you still remember growing up, where you hold the controller.
I have one. Yeah. I had the Wii U also.
Yeah. With respect to the TV, it knows your position and your location with respect to the TV. I mean, those are the things that we do. I mean, if you think about it, a lot of our sensors, we just not only make sensors for the traditional, more CIS kind of business, for surveillance and security, your security camera at home that you use. But actually I would have to say a big part of our product portfolio is including image analytics into the sensor, which is good for low power. And it's kind of like I would kind of have to say it's kind of like a trick parts for sensor, right? Where a lot of times we use optical as a solution to actually solve some problems that you can't do with a traditional off-the-shelf like 5 or 8 megapixel camera.
Yeah.
Because there's no shortage of resolution, as we know.
Yeah, no, I mean, that's what cameras pretty much, it's funny that, we kind of peaked at resolution like a decade ago.
Yes.
But, being able to process the image and actually do something with it, that's where we want to go into now. That's where we see this huge growth in AI, IoT microcontrollers, is the ability to do useful things with that, but then also achieve a good battery life.
Yes, exactly. Which is what we focus on. I mean, if you imagine the very, very beginning of the business where we started with optical mouse, I mean, when was the last time we actually changed a battery in our optical mouse, right? I mean, that's the one thing that we want to achieve with like battery powered devices, not just for mouse, but for everything else.
Yeah, but it's kind of what you need though, because like when you put, your AA, what is it? Just one AA battery into a mouse, like my Logitech mouse. I forget when I recharged that, if I ever changed it in years. And it's great though, because that's what I want. Like, this device to just be, wireless and able to be used. And I'm not thinking so much about constantly replacing the power and charging it all the time.
Yeah, perfect. That's actually the exact market that we want to serve. In terms of battery power devices. And now with the trend in AI too, I mean, we have seen a lot of up and coming use cases like for AI glasses, for example, right? Things that are portable, and it's really interesting to see the convergence of the innovation in batteries and also the advancements of AI, and now what it's actually able to bring for customers, and just creating useful features for our consumers at low power, and at the same time useful to the features that are useful AI-powered devices to the consumer. I think that's the key.
Yeah. I would say it's actually quite important now. So, we've got our new platforms coming out. OpenMV, for example. We actually have 2 new systems that we're going to be bringing to the market this year. The first one is the OpenMV N6. This is a new AI microcontroller that features the Pixart Imaging sensor. We're using their global shutter sensor, more or less. And this gives you color global shutter options. But we also have, let me get this guy mounted up there. It stands up like that. We also have a smaller camera called the OpenMV AE3. And this is also using the same global shutter sensor. But now we've shrunken the whole system to the size of 1 inch by 1 inch. Yes. So super tiny.
Yes, it's very, very small. And wow, I mean, the amount of things you're able to pack on this 1 inch by 1 inch is amazing, actually.
But one of the interesting metrics on this board is the whole system. It runs YOLO V5 at around 25 frames a second or so. And it only draws, though, about 60 milliamperes at 5 volts. So that the math, 60 to 50 milliamperes, it kind of oscillates up and down.
Sure.
But that's about 0.25 watts of power to run full 25 frames a second YOLO, tracking objects and such.
Yeah.
And then you're able to do the business logic and see where things are and follow them and et cetera without too many issues there. And what's interesting, one of the bigger things that we noticed there is that the power consumption of the sensor, that's really what allows us to achieve these low numbers.
Yes.
You might not think about it, but if you look at like a sensor, sensors are actually very complicated nowadays. Well, they used to be. Before you had the ISPs integrated into processors. You might look at an older sensor like the OV5640, which is ubiquitous on cheap IoT devices. And that sensor actually has a 1 gigahertz effective, 800 megahertz PLL inside, and with a whole bunch of digital logic. So it's actually a very, very complex system. And because of that, though, its power consumption is actually non-zero. Just to say it like that.
Yes.
Like it's its own digital processor.
Yeah.
And so as we move towards these sensors that are just giving you the raw data coming out of the camera, going to a processor, you actually want to get that sensor power down because it actually makes up a non-trivial part of your power consumption for your whole system.
Yes, you're absolutely right, Kwabena, because actually this kind of brought me back in time. So you remember when we actually participated in the Tiny ML, where I was giving a talk about the next frontier of CMOS imaging sensor. And you brought up a very good point, is that CMOS imaging sensor traditionally has always been focused on packing the most resolution into a particular form factor. And its main objective is really to give you the best image quality, vivid images that you want in terms of color, so that people look nice and pretty, right? So, but I think we have actually kind of gone past that innovation because we have done a pretty damn good job in it. I mean, with a lot of vendors, absolutely, right? But throughout that whole process, and I can tell you that because personally, I was one of the employee at one of this company who is pushing for the largest form factor of higher resolution out there. Power was never a consideration. I mean, it has never been, because the use case back then was always when you need it, then you turn it on. And you take a few snapshots and you turn it back on, right? So it's not really a big implication on the power per se, right? But however, if I were to look at a lot of these sensory inputs that we have, even back a decade ago, especially in the MEMS industry, they have always been always on, right? They have always been constantly tracking your motion, for example, but just never sensor. I mean, we are never able to get image sensor to be in always on sensory input to this bigger sensor fusion environment of the system. And I think people are starting to pay attention to it now more because of the fact that, like I said, the convergence of the battery advancement, right? And also these AI-powered devices that in a lot of cases that we have actually helped our customers, the sensor doesn't have to be 100% fully functional all the time, right? And that's the difference now, is that the sensor has to be working part-time, but it still needs to be needs to be able to get into a fully functional mode in the quickest with the lowest latency. I think that's the key.
Oh no, absolutely.
Yeah.
But it's really going to enable a lot of applications.
Exactly.
I think the way to think about this is, imagine this little camera. This is really going to be, our goal is to make these new OpenMV cams we want to make them as ubiquitous as fire alarms. You put your fire alarm on the ceiling and it's monitoring, smoke. But now we can have a camera monitoring their environment, tracking how many people are entering a room. Instead of using a PIR sensor that detects motion, and then when you're in your chair spinning around because you're bored at work, or so on and so forth, it's constantly turning the lights. Well, I think that the actual key there is, you've ever been in the office and you've been working, and you stop moving, you don't get up for like an hour and the lights turn off on you, and you feel like you failed at life because you're stuck in the office. But I mean, now we can actually have smart systems that actually identify that person there. And even better, though, they can be deployed, put into the office, put into the physical environment without requiring wiring. This is the huge key point. Where you see a lot of projects fail and where they don't get deployed and where things get sticky is, we look at the technology and say, okay, we got like a $100 PCB, it's got some CPU, it's got all this cool stuff, great. We turn that on, we're going to plug it into the wall, and we're going to use the AC power adapter. But hey, it's on the ceiling. And we're professionals, so we're not just going to have wires running through our ceiling. We need to run conduit.
Exactly.
And then you're looking at an install cost.
Yes.
And, I'm on the HOA of my condo, and we had to install some Hikvision cameras. We just wanted to add a few more. And the cameras themselves were like maybe $400, but it was a $5,000 install cost to run the conduit for them.
No, you're absolutely right. I think that also speaks to the trend why, when it first came out, I think back in the early 2014, 15, it's like the Arlos were doing so well. I think that's exactly what you're saying, right? The battery-operated devices, home security camera, I think they were the first one, right? Because it takes a lot of the installation headaches out of the equation. And now, all of a sudden, everybody can install a camera in their room, outside of their house, and whatnot. Now, so it just takes away that barrier, right? And I think since that time, people are starting to got the notion that battery operated devices is really the way to go to reduce any kind of barrier. Yeah. Where it's like, you don't need installation. And that's when I think it's really a good time for us. And that's when we met in 2019 talking about the next frontier is really we want to kind of enable the market to start thinking about some of these applications that you can do. Just like what you're saying is that the sensor itself is just outputting data, right? I mean, yeah, we have some image analytics in there, but still, if you want to have to scale to the different applications, you still need a very low power ISP or MCU at the back end to actually process this data to give you something useful.
Yes.
And that's why our partnership with OpenMV is very important, because I need to have a platform in order for us to do that, because just a single component, a sensor itself is not enough. We still need the back end to be low power too.
Yeah, and what we're trying to do at OpenMV, just to tell the audience about us. Yes. So what we've been making are computer vision cameras that are running on microcontrollers. The big point here is that because we're using microcontrollers, we have the ability to instantly turn off and on. And we also have the ability to keep the entire application image more or less inside of the MCU's internal flash. Yes. Or if it has an external flash that it's executing from just one device. Yes. There's no need, though, for a giant, DDR4 SDRAM, which draws a lot of power. And there's no need for a massive, multi-gigabyte eMMC drive to store the operating system image. And so when you look at being able to cut those two components out, that means we're saving a physical board space. Yes. We're saving the cost of those components. We're saving the power consumption of those components, and we're saving the heat generation of those components. Yes. So this allows you to kind of win in 4 dimensions at the same time. The benefit is you can build then a 1-inch by 1-inch camera that has 200 gigaflops. Well, gigaops, it's a 8-bit integer math, but we're using the ARM Ethos U55 processor, 85 in the future. And this, it gives you 200 gigaops of neural network compute. And it can actually execute models in place off of a OctoSPI flash that's attached to the board. Okay. And so this means that we're able to store multiple megabytes of models that are executed in place. And then the main chip here has 13 megabytes of RAM on chip in a 6x7 millimeter package. And that allows us to do all the tensor operations on chip, produce the results, and then have those, have your detections from like a model like YOLO. And then being able to run the analytics on board, figure out what's going on, like, do I need to count the number of people in the room? Yes. Or maybe count the number of people who've crossed a virtual line in the picture. And then because we added stuff like Wi-Fi and Bluetooth on board, the ability then to connect to the network and transmit that data and then go back to sleep, which is the key component. True. I was doing some numbers last night actually for this. And so I think our superpower is the ability to be in deep sleep mode, which that's about like a 50 microampere or less current draw for the whole system. And then the way you kind of build these things, it's all about how long you can stay off and how long you are on. Yes. And so you might look at it as, okay, I turn on for 5 seconds, and that's the boot. Boot. You're up within 1 second. You have your application running. You sense for maybe 1 or 2 seconds to figure out what's going on. And then you go back to sleep. So you're looking at maybe 5 seconds of runtime. And then you do that every 10 minutes or so. Yes. And that allows you then to sense the environment, but still achieve like a 5-year battery life.
That's very, I feel like we're speaking the same language, because it's something that's very important for our sensors too. When we design our low power sensor, a lot of times in the more traditional world, right, where the use case is really to turn on the camera, take a snapshot, and go back to sleep. And whatnot. There's only sleep, power off, right? And fully functional on. Right? But a lot of sensors we actually built in different. We have at least 4 to 5 different modes of power down. And that's one of the. If I were to look at how we are able to actually do so well in our optical mouse market, being a battery-operated devices, is that we are able to just, I mean, when the mouse is asleep, it's not moved for 5-10 minutes. Once you touch it, it turns it back on in the with the lowest latency possible. And through that 1 second of time, it probably went through like 3 different cycle level up. And I think one of the key that I've been in the imaging industry for a while that I've seen Pixart is really good at. It's simple enough to put on paper that you can turn it on and off your camera like without any side effects. I have to say Pixart is probably one of the best in doing that because of our experience in dealing with the battery powered devices. Because we need to, right? A lot of image sensors these days, and this is more of an older problem back in the days where it needs some time to actually cycle through in order not to have any ghosting image from the previous frame. We got rid of all of that. We solve all of that in our Pixel, so we don't have that problem. I think we are able to turn it on and off. And like you say, you brought up a very good point, is that majority of the time a device doesn't have to be on.
Yeah.
But how you turn off and on is really the key to saving power.
Well, there's also another. Well, I want to dig in on that point again because that seemed actually pretty interesting technically. Can you talk a little bit more about what you mean by you're fixing the ghosting issues in pixels?
So, a lot of times when you don't have enough. So on a pixel level. When you want to clear a pixel, you have to hit the reset gate.
Yeah, and that's I believe the way cameras work. It's like the opposite of the capacitor. You're charging the capacitors up, and then they get decayed.
And the decay, and that's the difference in the decay is really your signal.
Yeah.
So you have to hit the reset gate, but not. I mean, being an electrical transistor, it's not always ideal. Sometimes you will take longer for certain transistors to actually clear. So the secret sauce that we have done in the sensor is that through process and design work on how the pixels are being turned on and turned off, we kind of have some skill set to actually not turn it completely off and not turn it completely on immediately.
So you're saying you can save charge and thus power.
Yes.
And this is every frame, basically, across every pixel.
Exactly. So I think that's the beauty of it, is that we don't actually have to turn on completely, and still be able to give you a very, very low power. And so that when something happens, it goes to the next stage, and then within the next stage, it goes to the next stage if there's more movement. So it senses, it's kind of like a feedback loop of what is detected. And based on that vector, we'll go to the next stage. Yeah. And if it's just like somebody bump on the table, you don't have to turn it on completely, right? So it just maybe, it stays there for another few seconds, and if nothing happens, go back to sleep again.
Yeah, I think that's really valuable though, because we actually looked at the power consumption on our new system, and from your datasheet numbers, we're about a third of the power consumption of that 60 milliamp, about 50 or so, 55, let's say that, 50 to 60. About a third of that actually just comes from the camera sensor when you're running. And so when we're in a low power mode, and let's say we don't need to actually do a full image, it's totally possible then that we can use your camera sensor to actually wake up the system on basic motion and then decide to actually go to full power and actually do the proper analytics on the image. But we could use cheaper methods to kind of scan it and see what's going on. Like the camera would just tell us that it's detected some motion happening, for example.
So the sensor 7936 has also a built-in some kind of SMD that we actually call smart motion detection. That essentially what it does, it looks at the pixel changes over frame, and it looks at it in a very scaled down resolution. Which essentially how you save power, right? There's also another thing too, is that we are able to skip like 8 times, bin like 4 times, so that we can get it down to the smallest possible resolution. And those are adjustable, by the way. And then from there, what you can do is you can look at, based on a certain threshold on the pixel, how many pixel count it has changed. And over what DN count that it changes, then you can actually set a
and then you
trigger.
can issue an interrupt to the processor.
Exactly.
And we did connect those I/O lines so that they are available. Yeah,
so
two of them.
that's exactly the right way to use the camera. And one of the advantages that we like to use global shutter in terms of for this kind of computer vision application is that you can duty cycle it very, very slow, even at 1 frame per second.
Yeah.
And just think about like the exponential decline in your power when you go from a full 720p down to, half of a quarter of that and another quarter of that. And then your power just drops exponentially. And that's how we are able to actually still be able to work in always on mode. And when needed, we can go back to the fully functional mode.
Yeah. But what's also nice about your sensors, though, is they actually offer the performance aspect, too, because it's not good enough just to be, hey, it's got great power consumption, but then the image is like, I don't want it. Sometimes there are some sensors out there that have great power consumption metrics, but the image lacks some finesse.
It needs to be at least crisp enough. But you brought up a very good point too. There's also a very interesting trend, right? I mean, we used to build like this megapixel resolution for like human consumption to see because we want to see the best possible pictures out there, right?
Yeah.
And highest resolution and whatnot. But think about it right now, and we've got a lot of customers coming to us saying that the power is off the chart because of the fact that they were using a 5 megapixel to detect a 1.5 meter distance because they said, oh, this is the standard off-the-shelf camera that we can find, which is true, is abundantly available in the market, but it may not be the right design option for you if you want to save power. Because like I said, those sensors were designed back in the day when the use case is only when you need it, you turn it on, right? Again, it's very different mindset. And I think that's really the key. And I think one of the advantage that I've been working with you for a while now, since our Tiny ML years, is that you have quite a significant understanding of cameras. And you brought up a good point, is that cameras can be quite intimidating because the sensor itself is just a chip, right? Without the lens, it's not called a camera. But without the lens, it's totally non-usable. And looking for a lens is an art too, because the lens needs to find the right CRA match. It needs to find the right optical format to cover the entire imaging area and what your field of view ought to be and things like that. And whether or not you need IR, cut filter and whatnot. So I think you have quite a significant understanding of the ecosystem, which helps, right? Which helps bring the camera to our developers that, this is able to capture not only a decent image, right? It doesn't have to be as high quality as your smartphone because that will cost you power, but it's good enough for a machine to actually know what they're looking at.
Well, here's the thing I wanted to mention about performance, which is it's actually the frame rate. So you could have a 5 megapixel image camera sensor. And by the way, just to mention, for the larger version of the OpenMV cam that we're going to be launching, so by default, we're going to sell it with the Pixart PAG 7936, which is a 1 megapixel global shutter color. So pretty awesome. But we're also going to offer a 5 megapixel HDR option as an upgrade.
I see, yes.
But the reason we decided to go with the global shutter by default is because it offers a default frame rate of 120 frames a second. This means out of the box performance, you technically can hit 120 frames a second. Now, usually you don't ever really hit that speed. You get like 1/2, but that's still 60 frames a second for most actual things you're going to be doing, which means lucid vision quality, the ability to track objects at high speed, which at the end of the day, if you want to do performance machine vision things, you care about the frame rate of the camera, not so much having huge resolution, but how fast you can actually process images and get the next one. Similarly, though, even better, the camera can go to the quarter VGA resolution. Sorry, you can go down to the VGA resolution. And at the VGA resolution, you actually hit 240 frames a second. And that's where we're talking. You know, being able to run at that speed, all of a sudden you have the ability to do stupendously fast things like eye tracking, being able to follow little, laser beacons or things like that. And this also gets you, and because it's a global shutter camera, you can trigger it. And so this puts you into the realm of being able to do stuff for factory automation. Like imagine you have a part flying by a laser gate. I think that's what they're called. anyway, like the gate, something goes by, you trigger, and you capture an image, you process it, make a decision.
Yes.
These are all very important. And when you're using a standard rolling shutter that's kind of been designed to take pretty images, they really aren't good at being triggered and being able to give you those fast kind of motion changes, which is what you need to actually make the system into a sensor versus trying to, you can think of it as like a lot of machine vision systems are effectively processing video real-time-ish versus it actually being like a sensor that it has a deadline on when it's generating the data and how fast you're able to process it.
Yeah. So that's a very good point. And because of the global shutter, because of the use cases in the global shutter that we actually in the market that we serve, a majority of it are actually in this kind of machine vision type of application. I can give you an example. The drone, for example, right? They use global shutter sensor.
Well, it's absolutely necessary there because you're doing all kinds of stuff. Yeah.
And we not only use that, we also use a smaller version of our global shutter sensor for hovering as well. And just think about, I mean, of course, you can argue that the drone, the highest draw power is probably the motor itself.
Yeah.
But everything counts. I mean, if you can run it from, if you can fly the drone from 30 minutes to 45 minutes, say that's a 15 minutes gain on your power, right? So it is. We designed it that way, and one of the reason why it also stems from the fact that some of our mouse runs at like 40,000 frames per second.
Yeah.
So that's the kind of timing that I think that's the black magic that we know how to work our pixels in such a way that we can run it really fast without any kind of side effects, turn on and turn back off, right? And without any side effects. I think that's more of a discipline that Pixart has actually been able to attain through our years of serving this market.
Oh yeah, well, I recognize it though because one of the things we spent a lot of time on for OpenMV is designing a really good camera frame grabber driver in our system. So we actually have a really neat architecture that we designed. It kind of rivals what you can do with Linux, but on an MCU. So what we do is we actually have a multi-buffer approach, where there's 3 different frame buffers. It's called triple buffering. And so you have 2 back buffers where every time an image is coming in, there's an interrupt-driven DMA accelerated driver where we get an interrupt saying, hey, frame's coming, and then we figure out all the memory locations, set up all the DMA controllers, and that image is just then brought in with 0 CPU overhead into a memory buffer. And then after it's finished, you swap to one of the other 2 free buffers. And then the processor is working on the third.
It's like a ping pong.
Yeah, but it's better than double buffer because when you're double buffering, that only allows you to handle. Sorry, let me just pull up the interview script real quick.
No problem.
When you're double buffering, you're only able to handle. If you fall less than half the frame rate in your application, you basically just lose half your FPS. So double buffering, if you're hitting 120 frames a second for your application, great. Otherwise, the next step is 60 FPS and below. You don't kind of seamlessly go down from 120 below.
I see.
So with triple buffering, though, you're able to actually kind of go from 120 FPS and move slowly down that frame rate until you hit 0 based on how long it takes for your application to run. So the benefit here, if that's architecture that we run on board our system, is that you actually can realize applications where you hit that 120 frames a second, or maybe 100 or 80 or whatever, or anything in between. But the idea here is we're able to actually process these images and use every single one coming in, giving you the lowest latency system there. And we always want to see a higher FPS coming in because it means that the time that event happened between when you're able to process it and then do something about it is shortened. And this is huge for, again, machine vision control, actually like being able to build the system as a sensor. I mean, it comes into play when we look at, I used to do DIY robocars. And so that was all about trying to follow a line on the ground. And, the more latency you had on how long it took an image to be processed and come in and then drive your motors, the more like a drunken sailor your system was. And it's all just based on your ability to tighten the feedback loop and really tune that in. That allows you to have really tight control and be able to stay on a line. And this is important because it's going to be useful for things like, let's say you want to control a drone and have its landing system activate correctly. You want to do different robotic systems, pretty much anything where the camera is being used as a sensor. Having that tight feedback loop and being able to get that that image in quickly, process it, and then get the next one makes all the difference.
You're absolutely right. I think you are kind of hitting the point is that a lot of this global shutter sensor is actually used a lot in this kind of computer vision. And like, I think one of the example that you brought up was like eye tracking, eye gazing. I mean, they're like micro movements, but you cannot, you can't be running too slow of a frame rate either, right? Which is why we see a lot of our global shutter sensor being used in the eye gazing. Well, the eye tracking is a little bit more accurate, but accurate comes at a price of power, right? And being AI smart glass that you don't want to carry around a big battery block, you need it to be low power. And we find that the global shutter sensor is perfect in this use case. We don't actually run it at even 60 frames per second. Some of them run it even at 30 frames, because you just need to look at where your eye is gazing, approximate location. That's really where you need to be focusing.
Now, I want to move on to a different topic before to wrap everything up. But I think that we can actually push the sensor to somewhere up to 480 though, a little bit. Is that right, or?
At a scaled down resolution, yes. At a scaled down resolution.
I'm not going to promise that we're going to offer that in our system, but
yes,
it can go faster though.
Yes, you can go faster, and it applies to a lot of the sensor in the market these days. Is that you have a full resolution, say for example 160 field of view. For example, anytime you scale down can be done in two methods, right? It can be either through binning and skipping, where you will still try to keep as much of the 160-degree field of view as possible. And if you really want to scale it down even more to achieve higher frame rate, you can actually do a crop after the binning. Okay, but the downside of it is you may not get a 160 field of view anymore. You may end up with 120.
But what's nice though is your sensors actually support that, and it's well documented.
Yes.
We actually have a feature called readout window. Set the readout window in our firmware, and I actually made this work with it was the OV5640. What we did is we set the readout window, and we were able to like make the res down to like 160 by 120, and then the frame rate spiked up to about 100 FPS for us. But that was a 5 megapixel sensor, barely, making it happen. And so if you guys, we should be able to easily achieve probably 500 FPS or higher, which would be really cool for, you'd be surprised. There's a lot of people who actually really care about tracking like IR lights really fast.
Yes. And that brings up applications that, we normally detect and try to track things what our eyes can see, right? But now, again, going back to the idea that a lot of these videos and images are going to be looked by machine, and machine can process things a lot faster these days, right? So I think that opens up new applications that you can do with precision, especially when precision is involved.
That sounds good. So to wrap it up, let's tell me about what you guys are thinking about in the future. Like, where do you see things going? Just give me an idea. What is Pixart focused on?
So I think we have been kind of true to our core. Our core has always been in image sensors and what we can do with image analytics. Okay. So for us, what excites us is really the like I say, the convergence of battery and AI. So I think that convergence has we're seeing a lot of these new applications, and we're actually nurturing each and every one of these creative applications out there. Anything that's portable, battery operated, powered devices, AI powered devices, we are talking to all of these customers. Now, where we actually think our majority of our market is majority of our product portfolio, our product planning is going to happen is we're still going to be utilizing our image sensors to do image analytics for this kind of new applications. And I think that the next thing we want to try to do from a company standpoint, we just had an announcement, which is like the PAC 9001, which is like, we call it a smart pixel. So I think the next thing we are trying to move is how can we further reduce the bandwidth that the processor has to deal with. Like, for example, right now, a lot of times we see image sensor just outputting a raw image, for example, and let the MCU handle whatever they want to decide, whatever they want to do analytics on. Right? Now, although we have shrunken the resolution from 8 megapixel to now maybe this more manageable 1 megapixel, which gives you more horsepower on the MCU. Now we want to further reduce that bandwidth that the MCU has to handle. And why is it called Smart Pixel on the 9001 is because we actually just output the differential pixel. It's like an event trigger sensor. Okay. The advantage there is now all of a sudden you don't have that many flops toggling anymore. Things that are those pixels that haven't been moved, we just set it to 0, and we only give you the outline. And what is interesting in the PAC 9001 is that we actually it's a 36 by 16 image resolution, so it's not like high quality enough that you could see an actual face. And that takes away the privacy, right? The privacy concern of having it in house. But just like you say, like, you know, anything with alarm, and it gives you a much more sensible sensing option with our low power sensor that actually determines the outline. You can train this outline of a pixel to be whether it's your dog, whether it's human being or something else that's just walking past, and whether to turn on and turn off the lights. You know? So the power management part of it, we see quite a bit of now.
What kind of power consumption are you looking at for that kind of sensor?
It's in the microwatts.
Microwatts, okay.
Yeah, it can output up to 1600 differential frames, 1600 frames per second.
Okay, yeah.
But in most cases, you probably won't need that kind of frame rate. So, like I said, once you drop the frame rate, the power drops exponentially as well. So we are seeing quite a bit of traction there, even for eye tracking, because once you're able to see the outline again. With the LED, right? Because what we have seen is that there are sensors that use photodiodes around the glasses, and they look at the tracking. They just track the eyeball, see where you're gazing, and now this gives them a lot more information to deal with, so they actually can more precisely know where you're gazing at. So because it's low power enough, so it's quite a popular devices that we're actually pushing right now.
So there's actually a really fun algorithm that I hope to spend more time optimizing this and making it faster, but it's called phase correlation. And it's a very unique algorithm in that you basically give it an image and you give it a previous image, and then it'll tell you what the pixel translation is between those two images are to the subpixel level. Like, it'll give you a floating point X and Y translation between two images. It works by turning the images into the Fourier domain. So you convert them both into the Fourier domain, and then you do a cross power spectrum, like a complex conjugate multiply. Anyway, the mathematics a little bit over my head. But when you do the inverse Fourier transform, you basically get an image out that, like, after you multiply the two in the Fourier domain using a complex conjugate and then do the inverse FFT, it basically produces an image where you have peaks. And the XY location of a peak basically says how many pixels the images were translated in the X and Y position from each other. But what's also interesting about this is that you can do a second step where if you do a log polar transform, where like you reproject the image as a radial circle, and then have the distance, like the X and Y, like the X becomes a radial, and the Y becomes basically log of it or so. It's called the log polar transform. It's actually quite funny. If you look at images that have been translated like that, you look hilarious. But no, it looks like your face is stretched on all kinds of crazy ways. But anyway, the reason I mention it, though, is that after you do the log polar transform on the image, then you try to do the phase correlation method again. That actually gives you the rotation and zoom.
Wow.
And so doing both of these operations, you can get XY translation, zoom, so distance, so Z translation, and also rotation. And so you can get 4 different parameters there. And this lets you turn a camera if you're sampling the frame rate fast enough, your camera can effectively be like
used to track Z direction.
Well, X, Y, and Z and rotation at the same time.
I see.
I don't think you can, given the camera image can only be rotated this way or that way. It can't track rotation like this, or like that. But it can, like this or like this. It can't do those. So you can get only rotation in one direction. But still, it's kind of like an IMU out of a camera at that point.
I see.
But using sensor fusion, you can bring in an IMU now, and the potential is, as long as you can hit this fast frame rate, being able to track all this information at once, you can potentially build a system that has the ability to, find its exact location in 3D space by just being moved around.
Yeah, I see. Yeah, so I mean, this is something of an interest to us, and we have always. I think that the market is always trying to use sensor to do something.
Well, it's like a mouse, but in 3D space,
Yeah, yeah, and when once you said something about X, Y, and Z, it's kind of like our vector, right?
Yeah.
In our mouse, we actually kind of predetermine what your vector looks like, so it correlates that with your optical, physical mouse on the screen, and I know the market has been in need of something to detect the Z direction very, very much, rather than relying on the stereo vision and things like that. So if we can do it with a single camera, I think for a while the face detection was kind of the face PHASE, the face detection, the face differences. They use it to kind of estimate the distance. I think that can only be done with kind of limited.
Oh yeah, no, it's not perfect. Phase correlation, because it falls off really fast as you get away from something, so it's not like very good.
Yeah.
But it's again about like the way I look at it. We had quite a few people who bought the OpenMV cam for doing drone track and hold, where you just have the drone the idea is you have a drone flying really high in the sky and you want it to stop moving, and so like the issue is the GPS isn't accurate enough.
Exactly.
And so the camera can actually be used to act as like a mouse.
Yeah, that's the market we serve, actually. You're precisely on point. That's the market we serve. So it takes that image of there, and it looks at what has changed, right? And if there's not much change within a certain degree, it just kind of holds it steady. And the hovering was very important. So that's the market we serve, actually.
Yeah. So these are all cool things. Anyway, I think this has been awesome. It's been great talking to you.
Thank you. And it's been an enjoyable partnership. I mean, it's been many years going, and I'm actually looking forward to this partnership on the 936, and looking forward to helping you and also helping us in a sense, because with this platform that's made affordable to the market right now, it gives developers a quick and easy way to actually evaluate something very quickly. And any way we can help, we're more than happy to work together with you and your team to get things going.
Oh yeah, no, we're super excited. We're going to be bringing HDR sensors to everybody on the market, global shutter sensors to everybody. Previously, the prices of these have been rather high. So we're excited to actually bring affordable, mass market, really good computer vision quality. Our goal is we want to move away from just basic rolling shutter and no special features. I think the time for that is gone now. And we think it's HDR or global shutter, and maybe one day both at the same time.
Yeah.
That'll be the whole
Hopefully, yes. I mean, still some development needs to happen in that regard, but we are constantly innovating in that direction. And one last thing I want to leave with is that among all the partners that I've worked with very closely together, OpenMV has a great understanding of cameras, and I think that's one of the advantage that I look forward to this partnership very, very much with OpenMV, because like I said in the very beginning, cameras could be quite intimidating if you don't know the right lens, what to pair it up with, and how to actually run it. It's actually really, really hard for developers to go and source a camera by themselves. And this guy right here, he did it all for you, right? All you got to do is just power it up. He even has codes, open source, and a lot of developers there in the community to help out with. So this is perfect for anybody who wants to utilize camera to do something that's AI-driven for battery-operated devices. This is perfect. I mean, he's already done all the hard work for you.
All right.
All right.
Thank you, Charles.
Okay. All right. Thanks a lot. Thank you.
Thank you.